Today in this video we will talk about non-uniform circular motion. So you are still moving in a circle fashion, but the speed is not constant. So for that to happen, then you still need your centripetal acceleration, so you keep in circular motion, but now you're going to need perpendicular tangential acceleration, right? The centripetal, that's radial, so radial direction and tangential direction. This is meant to be 90 degrees. This is meant to be a circle. So that's it. If we have the total acceleration then composed of a radial component plus a tangential component, well then the total force, right, the total external force must be also composed of a radial component plus a tangential component. Remember the sum of force, that means the net force, right? There you go. So what means is that you have two components of the force that will give you a net force, like I could put it here somehow, maybe in green, right? This acceleration plus that acceleration gives you a net acceleration, which is related to the net force. So basically, again, we have forces in an axis perpendicular to the other, and instead of using I and j, or x and j and y, you will use perpendicular to the parallel to the radius, parallel to the tangent, right? So your axis is rotating at all times, depending where you are in the circular. Where you are in the circle. If you're here, well, your axis looks like this, radial tangential. If you are here, then it looks like this, radial tangential, right? If you're down here, radial tangential, radial tangential. That's an R. So just like what we did before in one of the earlier chapters, your reference axis keeps rotating with the particle in circular motion. Let's do an example. We're going to consider this example. It is the same mass with a string we already discussed in class, or in the past, actually in the last video, with the conical pendulum. But now, instead of the pendulum moving in circular motion on the horizontal plane, now it's moving on the vertical plane. Same string, same mass, but now vertically. So what we have at any given point with an angle theta, let's do this guy here. Let's do this guy. So we have the string, so that means we have a tension. And then we have a weight, which is pointing downwards. Because the theta also lives here, I can decompose the weight into two components. One parallel to the radius, which is mg cosine of theta, which is this, you see this is the radial direction, and then mg sine of theta, which is the tangential direction, right? This way I don't have to decompose the tension. The tension is of course always in the radial direction, while the weight, of course, will have two components. So then we can add all the forces in the radial direction, and what we will have is tension going up minus mg cosine theta, and this must be equal to the total radial force, which of course we know is mass, the mass of the ball, times its centripetal acceleration, which of course we also know is mass times v squared over r, right? Now, if we do all the forces in the tangential direction, well, notice that at this point, we only have one, which is mg sine theta, and this must be equal to m times the tangential acceleration, wherever that is. As we observe here, the questions are determine the tangential acceleration, which is this term, and the tension in the cord, which is this term. So we have two equations, two unknowns. We are supposed to express the tension in terms of the speed of the sphere, okay, for all angles theta. So if I call this equation 1 and equation 2, well, from equation 2, we get directly that mass cancels and the acceleration tangential is g sine of theta. That's one of the questions they asked. So look how the acceleration is not constant. G is constant, but the angle is not. When theta is 0, or when theta is 90, when theta is 180 or 270, well, the acceleration is changing. That's why if you have acceleration tangentially, that's why you have non-uniform circular motion, meaning the speed is not constant. So we got this from equation 2. From equation 1, we see that v from all this whole term, right? We see that the tension is equal to mg cosine of theta, which is this term, plus mv squared over r. I am going to do something here. I'm going to multiply this term by 1 in the form of g over g. What this will allow me is to factor mg, and this is going to leave me cosine of theta plus the m, I get it out, the g, I get it out, v squared over r, rg. And this is the tension, which, as we can see as well, is not constant. The mg is constant, v squared rg, and then look at the cosine. The cosine of theta, well, of course, is not constant because theta is changing all the time. Something else that is not constant is the v here. How do I know the v is not constant? Well, because there is tangential acceleration in this direction. So it's speeding up, slowing down, speeding up. The speed, we know the velocity is not constant because the direction is changing, but nor is the speed. The magnitude is changing just because there is tangential acceleration. So these are these are basically the answers already for this problem. We can go a little further and evaluate. I'll do this in this corner. I'm going to evaluate what is the tension, for instance, at the top and the tension at the bottom. When we are at the top, what happens? Well, at the top, notice that theta measured from here is 180 degrees. Okay, so if I take this answer and I say, what is the tension at the top? Well, it's going to be mg, then cosine of 180 plus the velocity, whatever it is at the top, square over the radius and gravity. And then what happens? What is cosine of 180? Well, cosine of 180 is minus 1. So the tension at the top is mg. And I'm going to flip this. V, whatever the speed at the top is, minus 1. Okay. If I repeat this at the bottom, the angle measured with respect to what they are doing in the figure, the angle is 0 degrees. So that means the tension at the bottom is mg. Following this, we get cosine of 0 degrees plus v squared over rg, which of course can be written as mg. This is 1, so v squared over rg plus 1. This is of course just the extremes for the tension. If you put 35 degrees, well, then you're going to substitute 35 here, and you are going to get the tension at 35 degrees. We still cannot solve this equation with numbers because we're missing some equations that I have not introduced yet. We're going to take a look at those in chapter 10. We can still do a little analysis, understanding what's going on with this equation. The tension at the top, right? You surely have played with something attached to a string and then try to move it circularly in a vertical plane. Notice that the tension is proportional to the speed. There is, well, here, this is the equation we're looking at. The tension is proportional to the square of the speed. If the speed is too low here, well, the tension is also going to decrease. There is a value for the tension, there is a value for the speed to which all this becomes equal to 0. And that is the minimum speed you can give to the ball at this position, and the ball still goes in circular motion. That minimum speed is when the speed is so low that the tension at the top becomes equal to 0. So I'm going to erase this because we don't need it anymore. I'm just going to make a little bit space here. If the velocity at the top is too small, so the tension is 0, then this equation becomes 0 equal to mg times v top minimum squared over rg minus 1. So notice that 0 over mg is 0, and this equation becomes v top minimum. If you solve for this, it's going to give you rg square root. So that's the minimum value this thing can have up here. So it still goes in circular motion. And if you go less than this, notice that the tension will become negative. And that's impossible because that will require the tension to be pushing, and you cannot push with a string, right? Negative tension doesn't work. Pushing with a string, and that's not permitted because the string can only be in tension, which means pulling. So that V will be the minimum value possible here. Good, we'll do a few more problems in class.